Alright, so today we're going to study the log-normal distribution. The best way to define the log-normal distribution is by this little rectangle. Whenever you see log-normal, you got to think of the random variable log of x, because it's the log of x which is normally distributed. That's the best definition of log-normal. All right? Everything refers to the log of x when we talk about the log-normal. So it's a little unusual in that sense. Typically, a random variable has a distribution, so it refers to it. But for the log-normal, you will see that all the parameters, for example, are defined as a function of log of x. So, again, best definition, log of x is normally distributed with these parameters, so lambda and psi square. Okay, so that means that by this definition, this means that lambda is the expected value of log of x and psi square is the variance, right? Because remember that for a normal distribution, the first argument is the expected value, second argument is the variance. So that is why. All right. Since it's the log of a random variable, log is always positive, so this distribution is only defined for positive random variables. So that makes it very useful for engineering applications because we typically deal with positive random variables. And these are the shapes that you see for the PDF and for the CDF. All right, so they all start at 0, and as for negative values, it's not defined, so it's going to be 0. All right, so that's the shape for different parameters, lambda, right? Lambda 1, 2, and 3, for a fixed psi parameter equal to 1. Okay, so you can see the type of, they're not bell-shaped, so now they're kind of skewed to the left, right? Okay, that's the PDF equation. You don't need to memorize it, but it's exactly as the normal distribution, right? Because of this definition. But except that instead of x, we write log of x minus the mean divided by the square. Okay? All right. Then, if we apply the formulas for mean and variances, we would obtain these two equations. All right? And if we take the ratio, right, so the square coefficient of variation would be the variance divided by the expected value squared. Turns out, so if you do it, you're going to find e to the psi squared minus 1, which can be well approximated by simply e squared or epsilon squared. Okay? But this approximation is good only when a psi square is small. Well, either psi square or delta square, right? And delta, remember, was the coefficient of variation of a random variable. And it's the same rule of thumb. Remember that we said for the coefficient of variation when it's less than 0.3 or 1/3, we will say that the variable has a moderate variability, right? So in those cases, if the distribution is log normal, it means that the psi parameter will have this will be equal, to the delta square coefficient of variation. Okay. All right, and let me say that this approximation is true because if you do a Taylor series of this, it's going to be 1 plus psi square minus 1, right? So that's why this approximation is useful. All right, and then we're going to see this is important too. We're going to see why in a minute. Okay, so just to recap, log-normal distribution means that the log of x is normally distributed with these parameters lambda and psi square. So what is unusual is that these parameters lambda and psi square do not reflect directly the random variable, but are the mean and variance of the log of the random variable. right? So that's a little bit unusual. Okay, so which means, let's go to the next one, that typically you're going to say, okay, this random variable is log normal, and then you will typically know the mean and variance of x, right? Mu and sigma squared, right? But lambda and psi squared are not the mean and variance of x, are the mean and variance of the log of x. So we need to do some more calculations in order to derive the parameters that we need, which are lambda and psi squared. So there's mainly two situations that are typical. So first is when you know the mean and variance of x. We're going to use the equations in the previous slide to solve for both psi squared and lambda, like that. Right, so first we're going to compute the coefficient of variation squared because it's given to you, right? And then we're going to compute psi squared because it's the log of 1 plus the coefficient of variation squared, right? It just comes from the previous slide. And again, when this coefficient of variation is small, then you can just say that psi squared and delta squared are the same. So in typical applications, when this is true, is that psi squared is the squared coefficient of variation. That's the best interpretation. Okay, and then we replace in the other equation for the expected value to solve for lambda, and this is the equation we would obtain. All right? And once you have the parameters lambda and psi, you can go ahead and compute probabilities, as we will in a minute. All right, the other typical situation is that you're given the median x of 0.5 and the coefficient of variation. This is the simplest case because you see again the same argument for psi squared is going to be the coefficient of variation if it's small. If it's not, it's just the log of 1 plus delta squared. But the other thing is that lambda is simply the log of the median of x, and that's coming in a minute. All right, so those are typical situations. But it's very rare that you would be given directly the parameters lambda and psi. So we have to go through this intermediate step. All right, but once we have these parameters calculated, then we go ahead and compute probabilities very similarly to the normal distribution case. Okay? And equation 4.8 is how we do that. All right, so the CDF of x, right? It's f of x equals this, right? And remember, it doesn't matter if you put strict inequality or not. Anyway, so here we can apply logarithm to both sides. We have the right to do that, right? And here's where we remember that the definition of a log normal in a variable is that the log of x is normal, okay? So this guy, log of x, as a random variable, is normally distributed with mean, lambda, and variance psi squared. So what we do is apply the normal distribution formulas, right? So this the CDF of the standard normal evaluated at log of x, which is here, minus the mean of log of x divided by the standard deviation of log of x. All right, and just because, again, log of x is normally distributed by definition. So that's pretty much it, my friends. Now, from here we can show this equation actually, right? Because let's compute the CDF for the median, right? So if I go f of x of the median, oops, I don't know what I did. Sorry about that. Okay, so the f of x, so the CDF of the median, by definition is 0.5, right? By definition of median. So the area to the left is 0.5. But this is also equal by this argument, right, is equal to phi of the log of the median. So I'm just using this formula right here. Minus lambda divided by psi squared, right, equals 0.5. Okay, but phi of something equal 0.5 means that that something has to be 0, right? Because phi, the function, the standard normal distribution, is symmetric with respect to 0, right? So if the CDF is going to be 0.5, means that this area is 0.5, right? And so you see here that the 0 is the value that would give you a CDF of 0.5. So this has to be 0. That's what happens. What's inside the parentheses, okay? And if this is 0, you see clearly that log of x of 0.5 has to be equal to lambda, which is what this result says right here. Okay? So that's the situation. So just to recap, the log-normal distribution is unusual in that the parameters of the distribution, lambda and psi squared, refer to the log of x, not of x. Okay. So that's why we need to go through these steps 1 or 2, depending on what information you're given. Okay, and then once you have the parameters lambda and psi, we go ahead and compute probabilities in this way. Very good. Yeah, so how to compute percentiles? Let's start here. So that's the formula that we're going to use. So that's the percentile of the log normal random variable, and that's the percentile of the standard normal random variable. All right, and you can see that this is because, again, the same derivation we did for the median, but we do it for any percentile x alpha, right? So you get to here. So this implies that this has to be, implies that this has to be zeta of alpha. That's kind of the key here. All right. So we know how to compute percentiles as well. Okay. So this is an easy one because so of course it's log normally distributed. They give you the median and they give you the parameter psi. So it's kind of an easy one, right? Because if they give you the median, the first thing you do, okay, lambda is the log of the median. And then they gave you psi. So you have everything, okay? So for the mean, what is the mean lifetime? Just apply the formula for the mean, which was in the first slide today. So it's pretty straightforward. Okay. This, yeah, I'll leave it up to you. This one too. There's nothing too special about it. Let's take a quick look at this one. Let's see what they give you. The seismic capacity, they give you the mean and coefficient of variation. Okay, so that was case 1 before. When you know the mean and variance, or mean and coefficient of variation, right? So, yeah, this is the situation that we're given here in part A, the mean and coefficient of variation. Therefore, we can solve for the variance of x, right? Okay, and then since that coefficient of variation we just calculated is less than 0.3, we can just assume that the parameter psi equals delta, and then we apply the formula for lambda. All right, so we obtain our values for epsilon, psi, it's supposed to be psi, spelled xi. for this guy. Well, it's not the random variable xi, it's just literally xi. Okay. Yeah, so the difference here is if you don't want to use this approximation, you also can use the exact formula for psi, which would be this one. So you see there's not much difference between 0.298 and 0.292. Alright, but then to calculate probabilities when we have f psi and lambda, we just go ahead with the normal distribution. But instead of 5.5 that we would do for the normal, here we just do log of 5.5. Alright? Excellent. And then a conditional probability, but by now we're experts in these things, right? Hopefully. Alright. And then, yeah, the calculation of the 85th percentile. Right, we're using the formula before where this would be the standard normal percentile, well, 85th percentile, right? It's 1.04. Very good. All right, now to the meat of our distribution. Why is it so important? Same thing as for the normal distributions, for the central limit theorem. But now, in the case of the log normal, is a central limit theorem for products. Remember, for the normal, let's say, central limit theorem is for sums or linear combinations. In this case, it's for products. All right, so a general product would be this formula right here for a U. Now, the symbol pi just means product. It's like summation, but product. So I can write it out for you. It would be x1 to the power of a1 times x2 to the power of a2 over a2 times xn to the power of an. Okay, that's what that means. Now the powers are the constant now, ai's. All right, and then you can see that any type of ratio or product could be expressed in this form, right? For example, when you have, oops, sorry about that. What's going on? All right. So if you have, I don't know, easy example, x1 divided by x2. So in this case, it's obviously a1 is 1 and a2 is negative 1, right? All right. And if you do square root of 2, that's going to be negative 1/2, right? So any sort of ratios or products with exponents you can do, that's where the central limit theorem applies for products, okay? All right, so what follows is almost, well, it is identical actually to the central limit theorem, but replacing mu by lambda and sigma squared by psi squared. Okay, so when n is big, so the variable u tends to the log normal distribution, log normal distribution with these parameters, lambda u and psi square u. And these are the same formulas we saw for the normal central limit theorem, all right? But again, replacing lambda by psi, lambda by mu, and psi squared by sigma squared. All right, so let me show you why this is the case. And these are the definitions of the A's and the lambdas, okay? But they're the same as before. Okay, now the covariance matrix that we use for the variances here is the covariance matrix of the log of x, right? Because everything refers to log of x now. All right? Okay, and as before, if the xi's have, you know for a fact that they do have the log normal distribution, then this theorem is going to be exact and not an approximation. Okay, so I'll ask you to please go through the proof and we'll discuss it during class if not, something is not making sense. But the key is this one. When you take the log of u, because u was the product, right? When you take the log, that product turns into a sum of ai times the log of x, right? And then that sum is a linear combination, and therefore we can apply the original central limit theorem, which would say that log of u has the normal distribution, right? And then the consequence is immediate, because here you have the case where the log of a random variable is normal distributed, and that is the very definition of log normal random variables. So that means that u is going to tend to the log normal random variable. All right? So quite an easy proof for this one. And here, as before, we show how this approximation works in practice. So here we have, this is the geometric average of the xi's. So it's the product, but all raised to the 1 over n power. Okay? So the first column shows you the distribution of each individual xi. So first is uniform, then is this one, like reverse exponential, and then the exponential distribution. And when you do the product of two random variables in this way, you see that for the first row it's pretty good approximation, but for the other ones it's not quite. But as soon as you have 5 for n, right? So when you're doing this product for 5 random variables, the approximation is quite good. Okay, so kind of regardless of the distribution of the xi, we have these good results. So it's a pretty powerful theorem. All right, so a fact that is very good to know for the log normal is that whenever you have a constant times a log normal random variable, right? Because here x is log normal, then y would be a constant times it. Y will have the log normal distribution with log of c plus lambda comma sigma squared, psi squared. Right? And the best way to see why this is true is you apply the previous theorem, but you consider c as a random variable with mean c and variance equal to 0. And then you're going to get this result. Right, so if I go back here, so you see here for the parameter lambda here of, let's call this lambda of u, right? Lambda of u is the expected value of log of u, is the sum of the AIs. Right, so if we replace this log of x by a constant c, you would see that you would have log of c plus all the other random variables. Alright, so that would give us this result. So log of c plus, and in this case we only have one random variable, so that's why. Very good. So now let's try our first example. So you see here, this is a kind of complicated ratio and products involving all sorts of stuff. We have a constant 7.58, so we're going to treat it like in the previous fact. All right, so let me write down here the AIs just to make sure that we understand what those are. So AIs are the exponents of each random variable. So x1 has exponent 1/2, right? This is the square root. x2 has exponent -1, x3 2, and x4 -1/3, right? The cubic root. So these are the AIs in our formula before, coming from the definition of U, okay? All right, so in this problem we have this, we have, we know that the xi's are independent, Okay, they don't say that they're log normally distributed, so it could be any distribution. But there's 4 of them, so we can apply this approximation, right? Or we will assume that CLT is going to give us a good approximation. Okay, so we're going to approximate the mean and variance of view here and a probability. All right, so central limit theorem, that's equation 4.3. Oh yeah, so here we had all the AIs. And then for each variable, we can compute the lambda and the psi in the way we did for the previous problems, right? Okay. And once we have that, we're going to apply the formulas for the central limit theorem. Okay. So the first one is for the lambda u. So the lambda parameter for the variable that we're interested here. So log of c, which and c is 7.8, right? And then plus all the AIs times the lambda i's, right? So these 2 columns multiply. And the same for the variance. So we apply the formula for the variance. Notice that typically you would have 2 times the covariance terms, right? The double summation, etc. But here they are independent, so all these covariance terms go to 0. Now, a typical thing with log normal is that they're always independent. It's very rare to see an example where you would have a covariance matrix with off-diagonal terms. Right, so it's simplified the calculation of the psi square. All right, so this should be pretty straightforward with this table and these formulas, okay? So once we have these 2, we can go ahead and apply the formulas for the mean and variance of a log normal random variable. So again, the first slide of today's lecture. Okay, and then part B is easy, right? It's just computing a probability. Okay, so make sure you practice that problem, and there's a couple more just like them that you can practice. Yeah, all of these are very similar. All right. We can talk about stock prices. This would be a very typical application of the log normal on the variable, because you see here the price of a stock, or really the price of anything, could be, you could say it's the original price plus the rate of return, so like the growth rate, right, in each year. These are periods. Let's say they're monthly or weekly. Right, so T is the period, time period. So after T time periods, you're going to have this much. And each of these RIs are the rate of return in each period. Right, so it's the product of random variables, right? It's the initial price, P naught, times the product of all these SJs. And the SJs, we call it the return of period, for time period T, which is just 1 plus R, right? So this would be S2, for example. Okay, so in this way, so you have a product, and what we think immediately is the central limit theorem for product, right? So here we apply the same formulas as before, right? So lambda t now, right? So lambda for the price at time t is the log of the constant plus the formula. Now, in this case, you have these, but these are just the lambda i's and the psi square i's, right? Now, in the case of stock prices, it is typically to assume that all these guys in the future time periods, right, because J is from the next week until the week you're interested in. So that's the future, right? Right now is time not, time zero. Not. right? T0 is the present, T equals 0 is the present, right? So we're going to assume that the future returns, they all have a common distribution. They all come from the same distribution, which you typically will estimate with historical data. Okay, this all to say that these are going to be lambda and psi squared constant like that. All right. And therefore, in this case, we have these two parameters. So for each year in the future, the lambda parameter has this form, right? So it's a constant times t plus lambda, so it's a straight line. And the same thing for the psi squared parameter is t times this psi square. Okay? So you could actually now do predictions of the stock price for future time periods, because for each future time period, you know the lambda and psi square parameters, just by applying this formula. Okay? So for example, this is how the log-normal approximation would look like compared to real data. Okay, so yeah, the bars are the real data and the log-normal would be the dashed line. You can also see that the normal approximation does quite a good job too. Alright? So yeah, we could actually use both, but for stock prices, typically the log-normal is the most used. Okay, and we can do a projection. Now, I did this back in 2018, right? But we could still compare it with the price of the Netflix stock today. So we'll do that during lecture. See how my forecast model is working. All right, so that's for the log normal distribution. Let's keep going. Let's talk about the next family of distributions. All right, so the Bernoulli family is, I would say, the first distributions that were developed, right? Because Bernoulli actually was a family of mathematicians, so they made very important contributions to our understanding. Okay, so that's why all of these random variables are of this Bernoulli family, and these include, of course, the Bernoulli distribution, binomial and multinomial, the geometric and negative binomial, right? So we're going to talk about these 5 distributions, and they're all related to the Bernoulli trial experiment. Okay, we talked about it in combinatorics, right? This is the simplest one. It's like flipping a coin, but the probability of success is going to be p, right? So values 1 and 0, and then probability of success would be p. These are examples, right? Okay, so we talked about the Bernoulli random variable before. Again, let's just define it again. This is the notation that we're going to use. That means that the random variable x has the Bernoulli distribution, and the Bernoulli distribution only has one parameter, is the parameter p, probability of success. Right, and this is the PMF, remember? So P of x is P is if x is 1 or 1 minus P otherwise. Right, and from now on we're going to use Q to stand for 1 minus P. Right, just like a shorthand notation. Okay, and then we already saw that expected value is p, and the variance is p times 1 minus p. All right, we've talked about indicator random variables. That's just another way of saying Bernoulli random variable, but it has the clear meaning that really you could define the success as anything. So here the success is the event A taking place, and A could be anything, right? That's why it's so general and useful. Right, so it turns out that the expected value of A is going to be P of A, which is the parameter, right? So that's a really useful property, that the expected value is the probability of the event that you're looking for. So we're going to use that in order to estimate these properties. All right, so the Bernoulli variable or the Bernoulli experiment is the basic experiment. And from it, we're going to derive all these new random variables. So the first one is the binomial, which simply is perform the Bernoulli experiment n times and count the number of successes. Okay, so you see it there in blue is the number of successes in n Bernoulli trials. And those are a few examples, right? But yeah, it's a really general random variable. It's because a success could be anything, right? A success is the event A occurring, and A could be any event of interest. All right, this guy has two parameters, n and p, and that's the notation. X is binomially distributed, so n is the number of trials, right? So the number of times you're going to flip the coin, and p is the probability of success, whatever you define as a success. Could be heads or tails, or voting for Biden or not. Okay. So PMF, let's talk about the PMF. And this is the reason we studied combinatorics actually, is for you guys to be able to understand the PMF of a binomial, among other things. All right, so for a binomial, right, let's look at this trial number line right here, right? So if you're gonna have X successes in these n trials, right? So and the successes are the arrows that you see here. So it's 3 in this case, right? Right. So if you're going to have X successes, it means that you're going to have n minus X failures. So the probability to have X successes and n minus X failures is this one, P to the X times 1 minus P to the n minus X, right? That's having X successes, because they have probability P, and then n minus X failures, right? And here we're using the multiplication rule for independent events, right? These events are independent because Bernoulli trials are independent, right? The result of one does not affect the result of the next one. And then the event that we're looking at here is having X successes and n minus X failures. And that's the probability of having such event. Then we're going to multiply by the combinations n of x and choose x. And the reason is that there's that many ways of obtaining X successes and N minus X failures. All right? That's the second interpretation of combinations we saw in combinatorics, remember, is the shuffling of identical objects. Here we have two types of identical objects. First is the X successes, and then the rest are failures, right? So the term here, P times 1 minus P, that is the probability of obtaining one particular arrangement. And the reason we multiply it by the n choose x, because that's how many arrangements you can make of X successes, which are all identical, and N failures that are identical too. Okay? So that's your PMF for the binomial random variable. And here you see some illustrations for different parameters, N and P, right? So the ones in the middle, you see they look very much like the normal distribution. Okay, so in fact, a very useful thing to do is approximate the binomial by the normal distribution. Right? Okay. These are the mean and variances. We're going to see why in a minute. Okay, and this is the CDF. Now, the CDF, kind of like the normal distribution, does not simplify. This is it. the summation of the PMF, basically, right? From 1 to x. There's binomial tables, but we're not going to use them, to be honest. You can compute this in your calculator. Most scientific calculators have all these distributions in memory. But in general, the CDF of binomial is not easy to work with, by hand at least. So that's why we're going to use normal approximations a lot. All right, why is it called binomial? Because of the binomial theorem. So it's right there in case you don't recall it. Okay? So notice that in our case, A would be P and then B would be 1 minus P, which is kind of weird, right? Because P plus 1 minus P is 1. But anyway, it's a true statement regardless. Okay, let's do this one. I think we did this before, but now we're doing it in the context of using the binomial random variable. So we are tossing 4 coins, fair coins, so the probability is 1/2, P is 1/2, and X would be the number of heads. Right? Okay. So here we're going to call a head is going to be a success, and therefore X would be binomial. X is binomial because it's just the number of successes in trials. So N is 4, and the probability of success P is 1/2 because they say that it's a fair coin. Okay? So those are the parameters. Okay, so yeah, here's the sample space of this experiment, right? And the bottom row is the number of coins. Sorry, heads. Right, so you could draw the distribution just with these numbers, right? Okay, but now we know that it's a binomial random variable. Therefore, the CDF and PMF are just the equations we just saw. Okay. So yeah, let's see. Right, part A is simply this one, right? It's just applying the same formulas, but with the numbers P equals 1/2. All right. And then yeah, we can plot them as we did before. Right, PMF, then CDF, and then part B, what is the median, upper quartile, right? So we know how to do that already. We start here for the median, for example. That should be 0.5. And go this way and down. Therefore, the median is 2. Like in here. All right, and yeah, the rest we know how to do it, right? Yeah, let's do the bonus during class. Let's see if yeah, let's see if somebody can come up with the solution for extra credit, right? Very good. Let me check the time real quick. All right, 2 more minutes. Yeah, it's important, is that the relationship between binomial and Bernoulli. So let's define a Bernoulli random variable being y, yi. And I is just the index, right? So we're going to toss the coin 10 times, so I will go from 1 to 10. Now, if you define the sum of the yi's, that's going to be binomial, right? Because it's the sum of the yi's, and the yi's are 0 or 1. They're going to be 1 when it's a success. So X is counting the number of successes, right? Take a minute to grasp that. And that's why then X is binomial, and X is the sum of Bernoulli random variables. Okay? So this is why we will be able to approximate the binomial by the normal random variable, because of the sum here. right? Whenever you see a sum, is central limit theorem. And central limit theorem is normal distribution. All right, let's leave it at that, and I'll see you guys in class.